All right, so tonight we're going to cover the topics of linear algebra and matrices and kind of see some applications of matrices and how we're going to use them in the future. So to start off, we need to first go back to kind of high school math and talk about solving a system of equations. So let's say I have these equations here. X plus y plus z equals 2, 6x minus 4y plus 5z equals 31, and lastly 5x plus 2y plus 2z equals 13. So do I have a volunteer who can solve this real quick on the screen? Does anyone remember how to do it?
I don't know about real quick.
Shouldn't take too long. Does that mean you volunteer, Beth?
Not necessarily. I'm trying to think about what I would do first.
We can kind of just talk through it. So what do you guys think I should do first?
I'll probably solve for one of the variables and plug it in.
That's what I was thinking.
Yep. So let's just solve for x at the top. So x is going to equal 2 minus y minus z. All right, and so now we can plug that into one of these two. So we'll plug it into the second one maybe. So 6 times this is going to give us 12 minus 6y minus 6z minus 4y plus 5z equals 31. We can condense this down, so 12 minus 10y minus z equals 31, and then minus 10y minus z equals 19. All right, so what's next?
Well, you could put, using this last equation that we just solved for, you can move either y or z to the other side and then plug that back in to one of the 3 equations.
Okay, so minus z equals 19 plus 10y, and then just reverse the sign. Z equals minus 19 minus 10y. All right, so now we've solved for 2 variables. So now what do we do?
Actually, I would plug this in right there.
Plug this into here?
Yeah, because then everything will be in terms of y, and then you can solve for y.
But since we used that equation to derive z, won't that mess us up?
Probably.
Just plug it into the first one since it's easy.
We can try that. So we'll plug in x too. Well, so if we plug in x, then x has a z in it. So we would have 2 minus y, and then we're going to minus a z, which z is this. So it's actually plus 19 plus 10y equals 2. And we just have to solve here. So we have 21 plus 9y equals 2. 9y equals minus 19. Y equals minus 19 over 9. And then we'd have to go back and plug. Basically, we'd probably want to utilize the third equation. But do you guys kind of get the gist of this? this is a little bit more of a complicated problem, so we can kind of just stop it here. But so basically you solve for two of the variables, and then you can plug them in the different equations. Since you have three unknowns and three equations, you know that you can find some solution. So let's go ahead and let's see, can I select? Cannot select this. Okay. So let's go ahead and clear it. And then, so now if we have that same system of equations, how could we write it as a matrix? So does anyone know what a matrix is? Can you give me a quick description of it?
I always looked at a matrix like a spreadsheet. It has rows and columns.
Okay. So you set it up like with brackets,
Mm-hmm.
and then you can have items in it like this. You can have any number of rows or columns. And then you can tell its dimension by rows by columns. So this would be 2 by 3. Okay, so with that previous system of equations, we can represent it using matrices. So our first equation was just x plus y plus z equals 2. So we can have a matrix that has all ones. And then the next row will be the next equation, and these were the coefficients, so 6 minus 4 and 5. And then the last one was 5 and 2 and 2. So we have that. And then we're going to multiply that by, let's see, our x, y, z. And then that's going to equal our products, which were 2, 31, and 13. All right, so that's basically how you could represent a system of equations as matrices. And here in a little bit, we'll see how you could solve it then using this matrix notation. All right. All right, so now we're going to dive into some Python, creating scalars, vectors, and matrices. We're actually not going to do tensors right now. That kind of comes a little bit later on. So we're just going to do those first three here. So you just need NumPy like usual. A scalar is basically a matrix that's 1 by 1. It's just one value. So we can create that here, print it out, and just look at what the shape of it is according to NumPy. So you can see there it is. It's like one number in brackets, and then the shape is 1, comma, nothing, because it's just one dimensional. And then a vector is basically like a line. It's 1 by some number of columns. So this would be a 1 by 3. And we can go ahead and create that here. And this actually made it a horizontal vector. So the dimension's 3 down here. And then similarly, a matrix, like you saw, it's kind of like a table. And this is how you make it in NumPy. You need big brackets like overall over the whole thing. And then each row you make like this. So you can see where the numbers end up. So each smaller component in here are the different rows in the final matrix. And then you can see the shape. It's just a 3 by 3. All right, so transposition is something you can perform on matrices. It basically means that you swap the rows with the columns. So the columns become rows, and vice versa. And if you have a NumPy array like this here, all you have to do is do .t, and that's for the transposition of it. So if we go back, it's this matrix down here. So you can see the first row is 4, 3, 2, then 7, 5, 1. And when we transpose it, then we have 4, 3, 2 along the columns, so on and so forth. So this will come in handy a little bit later on here. So now some basic operations with vectors and matrices. So if we're going to add some vectors together, let's go ahead and create, this should be a matrix addition, I think. So create some random matrices here, and then you can just do it like a normal number in Python, just put a plus sign in between. And it basically goes element by element and adds the two elements together that are in the same position. So the upper left and the upper left all the way throughout the table. Pretty straightforward. We can also add a vector and a scalar. So we have a scalar here, and then this should be a matrix and a scalar. So we have our matrix, and then we have a scalar. It's basically just going to add that scalar to each element. All right, so matrix multiplication. This is where things get a little tricky because there's a couple different ways you can multiply matrices. So the first would be kind of what you would think you would do, and just that you multiply each element by the same element in the same position. So this would be our A times B. If we go back just for reference, let's see, where was B? So this is A and B. So normal, just plain old multiplication, you would think, you know, you multiply the 4 and the 2, and then the 2 and the 6, and you end up with a 3 by 3 matrix again. So we can just confirm that here, and yep. So you don't really use this too often, but it is still available just by doing the asterisk there. So the most common multiplication for matrices is the dot product. You're gonna see this a lot. So to do a dot product, you have to satisfy a couple conditions. For the matrices, first of all, the order matters. So you're gonna have a matrix A and B, and the columns of A have to be equal to the rows of B. So if our A is a 2 by 3 matrix, then our B matrix has to have 3 rows, and then it can have any number of columns. So we could put like a 4 here. So just to see what this looks like, 1, 2, 3. So this would be A. And then B here would be a little bit bigger. Let's see, 1, 2. All right, so since the inner dimensions here, so the columns of A and the rows of B are equal, then we're allowed to take the dot product of this. And one of the properties when you multiply dot products, to figure out the shape of the resulting matrix, you basically combine these outer dimensions. So our resulting matrix is actually going to be a 2 by 4. And so with that in mind, we can kind of figure out how we would multiply this. So we're going to have 2 rows and 4 columns. So from matrix A, we're going to, let's see, multiply. Freezing. Good question, Beth. Let me get to that a little bit later on here. Here, let me see if I, okay. So it's going to be a 2 by 4. So actually, let's start off with a little bit simpler. So let's just do like 1, 2, 0, 3, 1, 2. So this is again a 2 by 3. And then we'll just do like a 3 by 2 to make it easy. So 1, 0, 1. All right, so this is 2 by 3, 3 by 3. So our final matrix is going to be 2 by 3 also. So let's plug this off. So you basically multiply, let's see, 2 by 3. So 1 times 1, and then you would do 1 plus 2 times 2 is 4, plus 0 times 3 is 0. And that'll give us our first term. So if you kind of saw how I did that, I'm taking, I'm going to cross the first row in matrix A and the first column in matrix B. So I'm multiplying here, here, and here, and adding them all together. And that's going to be the first term here in the upper right. So now I keep the same first row, and I basically multiply it by the next column. So here I'm going to have 0 plus 2 plus 0. And then I do the third column. So you can kind of figure out what that would be. But then basically I go down to the next row, and then I multiply that across. And at the end, I will have a 2 by 3 matrix. So the thing to keep in mind is just like this rule. Like if you can kind of figure out what the final shape of the matrix is going to be, you can figure out how the multiplying is going to go. But basically for column A, you go by the across the rows first, and by column B, you go across the columns. Does anyone have any questions on that? All right. And yeah, so the final product has shape equal to the rows of A and the columns of B. So to do this in Python, which you'll probably almost always do, you won't do this on paper too much, we can create two matrices here. So the first one is a 3 by 2. The second is a 2 by 4. So they can be dot product. And all you do is A and then dot and then B. And we get this result here. So now just to prove a point, the order matters. We can do the opposite, B dot A. So do you guys think this will work here? Can we multiply B dot A?
It won't work.
That's correct. Because if we reverse these, B is a 2 by 4 and A is a 3 by 2. The inner dimensions are 4 and 3. They don't align, so it can't be done. So that's an important property to keep in mind. Another multiplication you can do is a matrix and a vector. So here we're going to make a matrix and a vector, and here they are. And you can do a dot product again. So the vector is basically a 1 by whatever. So if we do this here, so the resulting matrix is going to be equal to the rows of A, and then it's just going to be one-dimensional the other way. So you have basically a line with the number of elements equal to the rows in the matrix. All right, and then there's also a dot product for vectors. So we're going to make two vectors here, and let's see. So when you do dot product for vectors, you actually get a scalar value. It's a little bit different of multiplication. The math is a little bit different, which I'm probably not going to show. But to do it in Python, you basically have to multiply the two vectors, and then you sum those multiplications together. So for example, if we take this away, we get this, and to get the final dot product, you just have to sum all of those. All right, so another thing you want to know about are determinants. So the determinant is kind of, let's see, let's first create this matrix here. So the determinant is kind of hard to explain visually. I have a really good video that shows it kind of on a graph. But one way to think about it is kind of if you have two vectors like this, it's kind of related to the area in between them. So if they're really far apart, the determinant's going to be higher, and if they're like more narrow, it's going to be a smaller value. And so for this example, the way to calculate the determinant here, let's see, you just you have to also go into NumPy, and then it's under the linear algebra module, and then it's just DET for determinant, and that will give you the determinant value. And then we can also do it for a matrix here too, and you can see what that gives you there. All right, and then the third type of multiplication is the cross product. So the cross product of two vectors will give you a third vector that's perpendicular to both of the original vectors. They don't really hit on this too much in the curriculum, but it comes up later on with natural language processing some. So definitely see it later. So we can create two vectors, and then it's just numpy.cross. And let me just go back here because this isn't going to show. All right, so when you do a cross product, you're going to get a new vector because it's a vector that's perpendicular to both of the original ones. All right, so there's something that's called the identity matrix. It's really important. It's basically, let's say I have a 3x3 matrix. The identity matrix would be this. So it's basically going to be all zeros except for the diagonal. So if it was a 2x2, it would just be 1, 0, 0, 1. And you can imagine for any size. So in Python, you just go under numpy.identity, you tell the size you want it to be, and it makes it for you nice and neat like that. So a property of the identity matrix and why it's important is that anytime you multiply a matrix by an identity matrix, you get the same matrix back. So it basically keeps the matrix and results in no change. So if we have this matrix here, A, and then we do the dot product of it with its identity matrix, we see that we get the same matrix back. All right, and then there's also the inverse matrix. This is related to the identity matrix because the inverse matrix, which is usually written as, so say we have matrix A, its inverse would be A to the minus 1. And the property of inverse matrices is that when you do the dot product of a matrix and its inverse, it's going to equal the identity matrix. So to prove that here, we'll create the inverse of our A matrix from before, print it out. It looks kind of messy, but when you multiply it and do the dot product with A, you see we got the identity matrix. I know there's some weird decimal points in here. This is just kind of a product of doing this in Python, but these values with the really small decimal places are basically 0. So just something to keep in mind if you see some weird numbers when you're doing this. All right, so now we're going to see how we solve systems of equations with matrices. So let's see, let's create some matrices here. So actually we can go back to the first problem. So I think it was 1's across here. So this is going to be for the coefficients. And then it was 6 minus 4 and 5. And then 5 and 2 and 2. And then our x, we're just going to leave blank for now. That's basically like our x, y, z. And then our final value matrix was, I think, this, 31 and 13. All right, so let's do some calculus here just to kind of, or some algebra here just to show how we're going to solve this. So basically we have our coefficient matrix A, we have our variable matrix X, and it equals our like product matrix V. So if you remember the property of multiplying a matrix by its inverse, that it equals the identity matrix, we can basically multiply both sides by the inverse of A, And then we would get the identity matrix times X equals our V dot the inverse of A. And the identity matrix times X is just going to be X. So X will be equal to V dot the inverse of A. So that's kind of the idea behind solving it. So now let's do it in Python. So all we need to do is find the inverse of A here. And then we do the dot product of that with V. And we get, this is the final result. So this would be X, Y, and Z. And I just want to test something here. Right, so the order here definitely matters. So it should be A inverse dot V and not the other way around. So this up here should be switched. So, because up here we're putting it on the left side. So here it would have to be on the left side as well. All right. And the nice thing about NumPy is that instead of doing that, you can actually just run the solve function in linear algebra. And there we get the answer that we got above. So this is the quickest way to do it. All righty. So now we're going to get into a little bit more of a complicated topic. We're going to use matrices to do linear regression. It's going to seem kind of like magic at first, but it's actually really cool. So here we have an example. This would be basically some data. So say we have, I don't know, let's see, we have the number of, let's see. Basically, here's our X data, 3, 4, and 6. And then here's our Y that we're trying to predict, 10, 12, and 4, 14. So we're trying to do a regression here. So, you know, we have our points like 3 and 10, 4 and 12, and then 6 and 14. And we're trying to come up with the line of best fit through that. So to do that with matrices, we first have to add, in order to have a y-intercept in here, we have to add a 1 to each of these. And then we create this matrix here. So this would be our x, and we know that our x times, let's see, know that our x times some matrix B will equal our target y. So the way to derive this then is a little complicated. Let me see here. So first of all, X is not a square matrix. So before, when we were doing like a system of equations, you know, we have like a 3 by 3 or a 2 by 2. And that let us just do the inverse and solve for our V really easily. But here we have, let me go ahead and display this. So this is our matrix. So it's not square. So we can't just do the inverse thing. So basically we have to find a way to make this square. And the trick to do that is to multiply it by its transposition. So we're going to multiply both sides by the transposition of X. This is Y. All right, so now we have a square matrix just like before. So basically, this is like our A from before, this is like our X, and this is like our V. So now we kind of do the same thing we did before. So we want to multiply this term by its inverse. And then we want to have this inverse multiplied by this side as well. And then when we do this, these two terms will cancel out and create the identity matrix, which is just going to be equal to B here then. And then on the other side, it's going to be the transposition of x dot x, the inverse of that. And then that's going to be dot the transposition of x dot y. And then I would obviously not matter there. And now we have our B. So that's kind of the math behind it. Hopefully you could kind of follow that. But so to set this up then in Python, we have this whole right side of the equation here. So xt.x is in here, and that's the inverse of it. And then we're dotting that with xt, and then also dotting it with y. So if we run that, we get our b here. And so this, the first term, since we put our y-intercept, our ones in the first position, this is our y-intercept. And then this is our coefficient for x. So let's go ahead and clear this off. So now if we plot this, it might make a little bit more sense. All right, so these were our 3 points. And then all I did was for each point, I plotted basically the line with the y-intercept, which was like 6 or so, and then using the coefficient, which was in the second position of our B matrix, times each value of x. And so that basically did a linear regression for that small data set. Does anybody, yeah, Bonnie?
So can you explain again why the X matrix you add a 1 there?
Sure. So it's basically to give it a y-intercept, to give it you know how like when you do linear regression and like stats models, you have to add a constant term?
Mm-hmm. Yeah.
It's basically doing that.
And the 1 need to be in the first place? Like cannot be like 1.
It could be in either one. We can go ahead and switch these here.
Mm.
Usually you put it in the first one, but it doesn't really make a difference. It's just going to switch the order in your final matrix or vector.
Can you tell me what those two numbers once again represent? So the second number represents the coefficient and the first number represents another.
Well, so we just flipped it. So if we reference back up here, we see that the second column is our ones. So that's our y-intercept, the constant. So that's what the 642 is going to represent. And then this first value is for basically our one feature, the coefficient of it. And it's going to be the 1.28. Does anyone have any other questions?
So you use like X transpose multiplied by X, right? And you take the inverse of that. It's a little bit fast when you go through that. Do you mind going through again the intuition?
Sure. So we have our feature column here, X, and then we have our coefficient B, and that's going to equal our target Y.
Mm-hmm.
So before, with the system of equations, we had square matrices, so 3 by 3, 2 by 2.
Mm-hmm.
That made it really easy to just take the inverse, basically multiply both sides by the inverse of X. But that won't work here because they're not square. So we have to find a way X square. So it's kind of just a trick. I don't know that there's a lot of intuition on why it works. I guess we could kind of think about it. So our X here is what, 3 by 2?
Yeah.
All right, so the transposition of it then, what shape would it be?
2 by 3.
Right. So that when it's multiplied, then the resulting is going to be square because it's going to take the outside.
Mhm.
So you multiply both sides by the transposition of x. And now you could kind of just cover up like these and think of them like before. This is just our a, our x, and then our v. So now all we have to do is multiply both sides by the inverse of this term here. So you have this term and its inverse times this term dot b, and then basically this inverse term again, and then it's just dot this term on the right.
And
And then
the reason why we're multiplying by the inverse is because we can't do division, right?
right.
Okay.
Yeah, so basically for matrices, like doing the inverse is like division if you were just doing a normal system of equations. So then since this is just multiplied by its inverse, that basically cancels out. And then our b is equal to this term here. And that's what this is in Python. So this part here is just this part, and then that, and then that.
Mm. Got it. Thanks.
Yep. Is everyone else cool with this? Somewhat?
Yeah, it actually answers my question from earlier too.
Cool. All right, I'm going to clear this if everyone's got it down, if you want to write it down. All right. So just one last note here. So this seems like a really cool and like quick and easy way to do a regression, but there is a problem with it in that it's really inefficient. So we've talked a little bit about complexity before of functions. Basically, you know, if you have a lot of nested for loops, the more you add to that, the time it takes to run it grows exponentially. And it's kind of a similar thing here because you're doing the transposition function, you're also doing the inverse. So this is kind of to show you an example of that. So when you do data science projects, you're going to have data sets with lots of rows and lots of columns. So in this case, n is basically the number of rows or the number of samples, and then m is your number of features. So in this first example, we have 10 features and we have 10,000 rows of data. I'm basically doing what we did above, finding that B matrix, and then I'm just keeping track of the time. This part in the middle here is just creating the matrices, randomize them in the correct shapes, and randomize like the target values because it doesn't really matter. So if we run this, we can see it's pretty quick. So let's add up to 100 features now. Still pretty quick. Now 1,000. Maybe a little bit longer. Now 10,000. You can see it's taking a while. I think this will take like 30 to 60 seconds. So we'll maybe give it a second here. But you can see how quickly it jumped up. It went from under 1 second, and then I multiplied the number of features by 10, and it's went up significantly. So a lot of the times doing a regression this matrix way is not very efficient, especially if you have a very large data set or a very large number of features. And I'm gonna give this a couple more seconds to see if it doesn't crash my notebook. I'd recommend not running this on your machine just in case.
Got 29 seconds over here.
Oh, yours is already done?
Yeah, mine was done in 20.
Ugh. I need a new laptop, guys. Well, I'll leave that run and go on here to the activity. So this activity is going to bring together a couple different things. You're going to have to kind of go back and kind of do what we did doing a regression using matrices. But this time it's going to be, instead of a regular like singular linear regression, it's going to be a multiple linear regression. So you have a data set here that's used to predict graduate chance, admission chance for students. And then you're given these different features. So like their GRE score, their GPA, their rating, whether they've done research, stuff like that. And then you're given a target column, which is admission chance. So the goal is to use the matrix method to do a regression on this. So build that regression, and then these are 2 new students. You're going to use the coefficients that you get from that B matrix to make predictions on their. So this is going to take a little bit of wrangling with the data set to get it in the right shape and stuff, but I think it's good practice for working with matrices and NumPy. And yeah, does anyone have any questions before we get started? I also think this finally finished. 85 seconds. Not very good. All right, no questions?
Okay, so the first thing that we did is we read in the data frame, and I read in the serial number as the index because that serial number is not going to have any predictive power. It's just basically which student is what. Then we set up our NumPy array. We noticed that this chance of admit column name had a space at the end, which was annoying. But we set up our Y, and the way that we did that is by passing in this chance of admit column as a NumPy array. Then we set up our intercepts, and the way that we did that was we set up a NumPy array of 1s that was the same length as our Y value. Then we set up our X values by again, passing in a NumPy array and dropping everything out of the data frame. Let me rephrase that. Dropping the target variable, so we had everything else. So basically, this Y value is now equal to all of this business right here. And then to put the intercepts plus all of the features that we wanted to look at together, we did this hstack NumPy function, which was pretty cool, and passed in our intercepts and our X values. And then to confirm that the array was the shape that we wanted and had all of the information that we wanted in it, we just looked at the shape. Then here we ran our crazy linear regression function that did all the inverses and fitted the matrices the way that we wanted them to look. And we passed that in as feature coefficients. And then these individual values in that feature coefficients are going to be equal to these. So if we wanted to call on any of these any of the features that we were looking at individually, we could do that. Then next we passed in our student 501 and our student 502 as a NumPy array. And then to solve for their chance of admission, we just multiplied basically this array here by each of the student arrays. And after we multiplied them together, using the quote-unquote Harmond product, we summed all of the variables that we got out to equal our target variable chance of admission. So student.
Beth, sorry to interrupt. So your first coefficient, that's the intercept, right?
Yes.
And when you create the student one, you create a 1 there.
Yes.
Okay.
And the reason why we did that is I was thinking like, how am I, because as you guys know, whenever you're solving for something, you have to add or subtract the constant. You're not supposed to change it, right? So if I'm going to be multiplying the student 501 times my feature coefficient, if I multiply the coefficient variable times 1, I'll get the same value. So student 501 has a 61% chance of admission, and student number 502 has a 92% chance of admission. Then to explore a little bit more, we decided to compare this, like setting this up to the OLS function that we've done in the past. And we actually got the same output here. Just now we know which ones have the various p-values that go with them too.
And the R-squared.
Yeah.
You technically could calculate the R-squared by hand with your like matrix results, but it's kind of messy, so.
Yeah.
All right, cool. Does anyone have any questions on this?
Yeah, so how did you guys do okay, so you did sm.ols, and then you just used your Y matrix?
Mm-hmm. And then Matt helped us set up this part because we wanted the constant as well. Apparently you can do statsmodels.add constant, and it'll add that one value in the front of all your constant, or add that one value in front of all of your features.
And you guys did it straight from the matrix or the data frame?
Straight from the matrices that we set up here.
Okay.
Yeah.
That was a much easier way to do it because I ended up having to try to parse out all the names that OLS didn't like to get to it. So I like this solution.
You can use data frame as well. I just used X. My X is the data frame of all the variables and then pass that. That worked too.
Yeah, but did you have to rename your column names for your data frame?
No, you just pass the data frame there.
Yeah, so you could do this. Some of the column, several of the column names actually had spaces at the end. So you could do, and then you could do.
Yeah.
Yeah. And you should end up with the same.
I guess you need a fit.
Yeah. Dot fit.
I think the issue is when you use the formula one. So here.
Yeah, I tried using the formula one and it wasn't pretty. Like we couldn't get it to work.
Yeah, because that's when it. So I remember this from our first linear regression project.
Mm-hmm.
So what ends up happening is extras like white space at the beginning are in, or dots.
Mm-hmm. It doesn't pass in well with the formula stuff.
Yeah, it doesn't parse well for some reason. So
Mm-mm.
I had to go through and rename all of them. And then I just did that again for this one. And I wish I hadn't. I wish I'd known this way to do it because that would have saved me probably 15 minutes trying to rename this thing.
Yeah, in the first project, I think I ended up passing in numpy arrays. I think it's what happened for me.
Yeah.
So yeah, that's our little exploration into multiple linear regression. This part to me was weird to think about, getting the sums.
Well, actually, I was talking to Bonnie about it. That's the same thing as if you did the dot product of the two matrices.
Right. Right. And I think that's because they're only one row, right?
Yeah, it's because of the shape. Your coefficients are just basically a vector.
Mm-hmm. So,
You end up with a 1 by 1 at the end.
right. So if this were like a tensor model, this approach wouldn't necessarily work.
Right, if you wanted to like pass in like multiple students or something.
Mm-hmm. Okay.
Or well, I guess in that case, you would just get an array back of 2 rows, basically. You would get both percentages back.
Right.
So that should still work.
So that would look something like,
I think you'll actually want to do like a V stack of student 501 and 502.
gotcha. So that would be NP V stack.
What is VStack?
So it basically lets you like append in a row like that way.
Yeah.
And then
So,
H stack lets you add the columns.
yeah. Okay. And then this would be, we would want sure times all students. Okay. And then,
So maybe try doing like the dot product. So do like all students dot feature coefficient.
dot, it's literally just dot dot, right?
Yeah.
Dot, dot, okay.
Cool.
So yep. So you could pass in like a whole data frame to make predictions on.
Hmm.
I know so many admissions counselors that want this right now.
Maybe you can help build it for them.
Yeah. Okay.
All right. Well, good job, everyone. Any other lingering questions? I did post in Slack just now a link to a YouTube playlist. It's 3 Blue, 2 Brown, if you've ever seen them on YouTube. Does a really good job of explaining like lots of concepts, specifically linear algebra in this case. Really good at the intuition behind it all. Has like good visualizations. So definitely check that out if you're still feeling a little confused on some of it.
Oh, I didn't realize I was still sharing my screen. All right.
All right.
Cool. Thank you.